There was a session on Saturday, but I did not get a mail. No, no, no. I sent a mail. I already sent a mail on Friday, most probably around noon time. But I sent a mail. That mail, I don't know why that mail was not sent from um, this NPTEL office, but there was a mail. I already sent that mail. Just one minute. I can show you. I think you can check. There was a mail I sent. Yeah, 13th September around 1:37. The problem from technical side. No, but I sent mail and that mail received, I think, in any forum I sent. Okay, but you can at least you can look at the recorded one. No problem. Yeah. Okay. Okay, my audio and my screen is visible, right? It is clear. Okay, so let's start. So this is tutorial 9. Tutorial 9. And what is the date? Oh, sorry, this is point set topology. Point set topology date. Today is 17th September. If you have any specific doubt regarding assignment 7, at least you can ask, no problem. But there was three questions left. Those problem I will discuss today. Okay, and after that I will discuss some theoretical part and some problem of content 8, which will help to solve problem of assignment 8, and which is supposed to be the submission date is uh, tomorrow, I think. So problem number 10. So I can assignment 7. Yeah. Problem. If you have any problem, any doubt, you can ask. Otherwise I'm just going to assignment 7 problem. This is not the assignment. This is 7 problem. But okay. This was this is the problem number um, 10, I think. Yeah. This is problem number. Most doubts are already cleared in previous session. Yeah, three doubts are there, so that I will be discussing today. But even if you have any doubt, I mean not understood anything of assignment 7, which was discussed in last session, you can ask, no problem. This is problem number 10. I'll try to. I mean, if you have any doubt regarding those problems, you can ask. I will try to cover rapidly. Okay. Okay. So what was the questions 10, that let D2 be the unit closed unit disk, you can look at, be the unit disk. Consider the equivalence relation on D2, which is defined by x related to y if and only if either x is equals to y, or x and y are in S1. S1 is the unit circle. Okay. Note that Note that S1 is equals to unit circle that x and y belongs to R square, such that x square plus y square is equals to 1. This is the, now where S1 is the unit circle, then the quotient space is homeomorphic to. So you can look at this. This question can be handled to the quotient topology. So let's recall the quotient topology of a recall quotient topology. Quotient topology. Okay. What quotient topology says is that let um, let X tau be a topological space, be a topological space, and this is something uh, relation on this particular set X. Then, and this is not only a just a relation, this is an equivalence relation. This is an equivalent relation. This is an equivalence relation. This is an equivalence relation on X. Then X mod this is mod, this is X mod this is the collection of, is the collection of all equivalent classes, equivalence classes. Okay. So now question is, this is a set X mod this X mod this tilde, this is a set. Now question was now how we can we give a can we give a topology on X mod tilde such that, first of all, okay, whenever there is a set, suppose X is a set and there is equivalence classes, this X mod, that I can give a map pi. How this map is given, pi of X is equals to this mod of X. What is this mod of X? That is the equivalence classes where X is belongs. Okay, every element of X, I mean, whenever I have an equivalence relation on a set, that equivalence relations will divide that set in some part, so each part is equivalence classes. So now every element should belong to some of the equivalence classes. So suppose X is an element. Now X should belongs to some one equivalence classes. So let that equivalence classes is mod X. So in mod X there should be any other point. There may be more point. Okay. So this is surjective. Is a surjective map. This is as a set map surjective. Okay. This is as a set map is surjective. Now question was, can we give a topology on X mod tilde such that pi from X to X mod tilde is a continuous function, continuous, and surjective is automatic. Okay, surjective by definition, surjective, continuous, and second is that for any, you can look at what is the important fact is that this pi, note that I can just here note that pi is constant on each equivalence classes. Equivalence classes. That means if I take two elements x and y from capital X, whose they are belongs to same equivalence classes, then their image under pi is same. So now the question is that any continuous function, any continuous function f from x to a y a topological space, y a arbitrary topological space I am talking about, topological space any continuous function. Note that any continuous function f which is constant on each equivalent classes. Constant on each equivalence classes must factors through uniquely factors through x mod by a continuous function. So what is mean this? What is the meaning of this? This meaning of this is basically that suppose I have x to x mod tilde. X is a topological space. It has a topology. I want to give a topology where x mod tilde such that pi should be continuous. First this pi, and for any map f which is from x to y and that is constant, that is continuous. First one is continuous. Second one is that constant on each equivalence classes must factors through X model. That means there should exist a unique and continuous F naught such that F naught is continuous first and the diagram commutes. This is written this way and the diagram commutes. That means F naught compose pi is equals to F. That was the thing. Okay, so that f naught will be unique. This sign is unique. Okay, there exists a unique. This sign is unique. There exists a unique. So what was that construction? Suppose I have an set a topological space x and I have a equivalence relations. That equivalence relations will divide the set x to an equivalence classes, and that equivalent classes set is x mod tilde. Now automatically I will get a surjective map pi from x to x mod tilde. That is that was that is automatically surjective, but continuity is not as a set map. So suppose if I have an function f which is from x to another topological space y which is constant on each equivalence classes, then that f should be factors through f naught. That was the and the topology on this topology on x mod tilde for which above two condition holds above two condition holds are is called quotient topology. Okay, and an interesting fact is that is unique will come from this particular way. But okay, the fact is that this is something called universal theorem, and this universal theorem you can encounter in many places like uh, abelian group. In case of group, in case of module, you will get this. In case of tensor product, there you will get this. All these things. Okay, similar type of things. But the fact is that what was the topology, and that topology is given by that topology is given by collection of sets. What is that collection? That U is subset of X mod tilde such that pi inverse U is open in X. That means here I have automatically a map pi from x to x mod tilde. We know x have a topology. Already x has a topology. We know that that topology is somehow there it is already, that is given from the beginning. Now I want to give a topology on x mod tilde. I want to get the collection of open sets. That was the question. So how I will get an open set? A set U subset of x mod tilde will be open if pi inverse U, that is an subset of x, is open in the topology of x. That was what. Okay. So that means this is open in, this is the collection. So this is the open set, and with this particular this is the topology of, I can write it at x mod tilde. This is the topology. So this set collection of sets will satisfy all other property 1 and 2. Okay. Now I will use this one. Okay. That's why I am just talking about all these things. And okay, let's D2 be the set, and here given that, let problem number, get back to problem. Okay. What are that? The D2 is given that close, and D2 is given that x and y belongs to r square, such that x square plus y square is less than or equals to 1, and equivalence relation x related to y if and only if x is equals to y, or x and y belongs to the same S1. That was the question. Okay, x and y belongs to the S1. S1 means that circle. So that was the equivalence relation. So question, so automatically I will have a topology quotient space D2 mod this tilde. Now question is that then the quotient space is homomorphic to whom? That was the question. Okay. So we know D2 mod S1. What is that? That is all xy belongs to R square, such that x square plus y square is less than 1. Okay, this is just open unit disk. That is all. Okay. D2 is equivalent to homeomorphic. This is not equivalent. R2 homeomorphic. How this is homeomorphic? The way how the 0 1 interval is homeomorphic to real number open interval. Similarly, this open unit disk will also be homeomorphic to S to R S1. So this will be homeomorphic to R square. Okay, via the homeomorphic map as okay. Now suppose I will give a map from S2. Let F is a map from D2 to S2. Define. It is not the define A from D2 to S2. S2 is what is S2 is basically circle in R3. S2 is subset of R3. Okay. What was S2? S2 is equals to x1, comma x2, comma x3 belongs to R3, such that x1 square plus x2 square plus x3 square is equals to 1. Okay, that was the x3. Sorry, that was the S2. Now we will give a map F from D2 to S2. How this map will be defined? That how this map will be defined? That is basically we know there exist okay, so that this is a okay, and we know there exists a homeomorphism G. I am taking G from D2 minus S1 to R square. Okay, okay, and R square is sitting R square is sitting inside S1, sorry S2, sorry R square is sitting inside R3. That is automatic. Okay, so basically map is something like uh, so how this f will be given? This f will be f of x, f of x. This r is sitting inside R3. This is automatic. Okay, this is something I can write it as inclusion. So f of x is equals to g I compose g I compose g of x if x belongs to D2 minus S1, and if x belongs to D2 S1, and this is 1 comma 0 if x s belongs to s1. Okay, is this map is okay clear to, I mean, how I have defined, is that clear? Okay, better to write define a map here. F, I'll write is F. I am defining a map F from D2 to R3. How this map is defined? We know D2 is D2 minus S1, that is open unit disk, that is homeomorphic to the R2. Okay, this is the homeomorphism. Okay, also R2 is automatically sitting inside R3, that is inclusion I. So I can give a map I compose this G, that is a map from D2 minus S1 to R3. So that was how this map is defined. So f is defined whenever x is coming from d2 minus s1. I have defined I compose g of x, and when x is in s1, so I will map to it is to 1 comma 0 comma 0. Then clearly they note that clearly f is continuous. Why this is continuous? Because I compose g is continuous first of all. Okay, I compose g is continuous. So F is continuous. Define F from D2 to R3. We know there exists a homomorphism G from D2 minus S1 to R2, which is sitting inside R3. G is continuous. I is continuous. That is continuous. That is for sure. But why it is continuous at the point x equals to, okay, that will be okay. Okay, so that is let's take this R3. This is not, this inclusion is, this is, I can take this R2 is sitting, R2 is homomorphic to S2 minus 1 comma 0 comma 0. This one. This is homomorphic to S2 minus 1 comma 0 comma 0. This is the set. This is the stereographic position. Stereographic projection. Okay. So this will be the Naka. Okay, this is the map. Okay, I got it, got it. Sorry for the. I got it. What is the map? That map will be something. This is S2. This is correct. This was correct. This will be like S2 sitting inside R3. That doesn't matter. But how this map is defined? F from D2. F is from map will be same. F of x is equals to, that will be f of x is equals to um, f of x is equals to phi compose. Suppose this is the homomorphism phi, stereographic position phi. Phi compose g, um, yeah, phi compose g of x if x is belongs to d2 minus s1 and 1 comma 0 comma 0 if x is belongs to s1. Okay, that is how it is defined. Okay, so basically basic idea is that suppose I have outer circle, I have a circle like this. I'll define points inside to the to another, to as it is point defined inside as it is, but I will define all other outside point, all other point to a single point. That is how it is defined. Okay, so then f will be continuous, then f is bijective, surjective basically, not subject. surjective continuous, and if is constant on each equivalence classes. It will be constant on each equivalence classes. Okay, if is not only surjective, okay, we don't need all these things actually. So, so if is bijective is clear, I think. Bijective and continuous from D2 to S2. Now, note that D2 as a subset is compact in R square as a subset, okay? And S2 is housed up. Then F is a homeomorphism. So D2 is homeomorphic to, no, sorry, no, sorry, please. I'm just making too many mistakes to okay. Sorry. If is continuous, that is your bijective, not bijective, surjective. If is continuous and surjective and maps equivalence classes to a constant, and F is constant on equivalence classes. F is constant and is constant on each equivalence classes. Okay, up to this point it is clear. So F is constant. So now what I have, this D2 to I have D2 to I have a map from this D2 to S2. I have a map F. Okay. Now already from D2 to this I have a projection pi. Now as F is continuous, then by the properties of cosine topology, by the properties of cosine topology, there exists a unique continuous map. There exists a unique continuous map F naught from this D2 mod tilde to S2 such that F naught composed pi is equals to F. This is the property I am recalling from this above thing. Okay. Then note that F being constant on each equivalence classes, equivalence or it how the note that how F is defined. The definition of F, definition of F says that F is bijective, not only bijective. So there exists a unique continuous function. So F naught is bijective and continuous map from this D2 mod tilde to S2. Okay. But what I need? Now I need to, if I want to prove that F naught is a homeomorphism, I need to prove that dt mod Z, S2 is Hausdorff and d2 mod Z is compact. That I need to prove. So, but note that. So how I'll prove? But note that pi from d to d2 mod tilde is a surjective continuous map. Okay, surjective continuous frames. So it should map a compact set. It should map a compact set to a compact set. As D2 is compact, pi of this D2 is equals to D2 mod tilde is also compact. That means this F naught from this D2 mod tilde to S2 is a bijective continuous map from a compact set D2 mod tilde onto a Hausdorff space S2. So that implies F naught is a homeomorphism. That implies this D2 mod tilde is is homeomorphic to S2. Okay, let's recall. I mean, good. What are the problem? Problem is that suppose I have D2. Okay, and consider the equivalence relation. What is equivalence relation? Says that x related to y, either x and y are same, not in S1. I mean boundary, or it is. I mean either they are in bound. If they are in boundary, they are in same equivalence classes. Otherwise, it is as it is. Okay. So now I have defined a function f from d2 to s2. How this defined? F of x is equals to phi compose g mod x if x is coming from not from the boundary s1. If it is coming from the s1, I am mapping it to the single point 1 comma 0 0. Now how this phi and g are given, that g is d2 minus s1 to r2. This is an homeomorphism, automatic homeomorphism, because that is d2 minus s1 is the open unit wall. So open unit wall is homeomorphic to R to the power n. So here it is also. So G is homeomorphism from D2 minus S1 to R2, and R2 is homeomorphic to S2 minus 1 comma 0 comma 0. So that means this phi compose G is a map from D2 minus S1 to S2, and that is a homeomorphism. So this is the way, and F is defined like this, and whenever x is coming from the boundary, then it is 1 comma 0 comma 0. That is not 4. So that means F is bijective. It is clear. Now F is continuous also, because this is constitution of continuous function. Now as F is continuous and bijective function, but I will use that continuous fact only. Then what it says, that quotient topology says that there should exist a unique continuous function f naught from this d2 to s2. Okay, that continuous function. Now how this f naught is defined, that will be depend. I mean this relation, that f naught compose pi equals to f. This relation will give that f naught is not only continuous, that is also bijective. So f naught is a bijective continuous function from d2 mod to d2 mod tilde to s2. We know that a bijective continuous function is homeomorphic when it is not only that, if a bijective continuous function from a compact set to a Hausdorff space is homeomorphic. So here S2 is Hausdorff, there is no doubt. But I need to prove that D2 mod tilde is compact. And how I will prove that D2 mod tilde is compact? Because pi is the map from this D2 to pi is the map from this D2 to D2 mod tilde, and pi is surjective, and pi is also continuous. So a continuous function always maps a compact set to compact set, and it is being surjective. Pi of D2 is equals to D2 mod tilde. So that's why D2 mod tilde is compact, and so F naught is bijective continuous function from a complex set to complex set. That's why it is homeomorphic. So that what it gives, that this is the relation S2 is the correct option. But why other option is not correct? Because S2 is not homeomorphic to S1, S2 is not homeomorphic to R2, and S2 is not homeomorphic to P2. Okay, so that's why they are not correct. As S2 is not homeomorphic to S1 or R2 or this, what was that symbol P, that is defining P2 or this is not homeomorphic. So that's why option A, C, D are not true. I hope it is clear. If there is any doubt, you can ask. Not true. If there is any doubt, you can ask. I hope this is clear now. Okay, thank you. Next is question number. Uh, Next is question number 11. 11. This is the question number 11. What it says, let G and B are two topological group. Okay, topological group. You know, topological group means that is topological space, and the group operation like x and y goes to xy and x goes to x inverse. These two map from G cross G to G, and here it is G to G. These two maps should be continuous. Okay, so that is then G, then the topology, then the group G with the topology is called a topological group. Okay. Now F is a map from G to H, be a group homomorphism. If F is bijective and continuous, then F is homeomorphism. Whether this is homeomorphism, this is true or false. The answer is false. I'll take that counter example given in the solution space. Let's take Z2. F is a map from Z2. Z2 is the just integer. Z is a map from Z2 to A plus B root 2. B root 2. AB belongs to Z. Clearly, F is bijective. Okay. In the subspace topology, subspace topology, and what is called, okay, just a minute. This is subspace topology, and so coming from the real number, coming from R2, which is discrete topology also. We know that Z has discrete topology. Subspace topology of Z is discrete topology. Similarly, here is also the subspace topology of Z2 is again discrete topology. But discrete topology is so topology is discrete topology, which is discrete topology. That is the important fact, which is discrete topology. This is also a subspace topology. Topology from real number. Okay. This is subspace topology for real number. That is okay. So now we know if okay, just let's fact f is a function from x to y where x has discrete topology, then f is continuous. How it is defined, that does not matter. Why it is happening? Because for every inverse, because in discrete topology every set are open set. Every set in X are open set. So if I take an open set in Y, suppose I have given a function f from x to y. X has discrete topology. Why have any topology, but I don't care right now. But so when F will be continuous, if F maps inverse image of every open set is open. So now take an open set in Y and take inverse image. That will be in X, but that set is already open because X has discrete topology, so every open set is open in X. So that's why it is open. So this is the fact. So this due to this fact, we can say that here F is open. So F is continuous function. Sorry, not open. Continuous function and clearly F is bijective. Okay. So if I take this is the set, okay, how this F is defined that I have begin by F of A comma B is equals to A plus B root 2. This is the set. So automatically bijective. Take any element coming from this A plus B root 2 this set. What was the element? That A plus B root 2 and B should coming from Z. So now A plus B root 2 and F is from AB2, so automatically any element will be like A plus B root 2 for which A and B should be coming from Z. So that means I will get an inverse image and this is automatically bijective. There is nothing, this is very clear. Bijective. But why F is not, but F is not homeomorphic. That is what I need to prove. But F is homeomorphic. Why F is not homeomorphic? This said A plus B root 2, AB coming from Z. This set is something like, just a minute, A plus B root 2. This set is, this is a special character that I want to recall. What was that? Is this set same with R mod Z? This set is not discrete. That is what I was trying to say. Okay. This set is okay. Sorry, I got it. This set will be homeomorphic to. I think this set will be homeomorphic to rational number. I think. And just a minute. Yeah, yeah. This set is homeomorphic to rational number. Right. That is what I am just saying. This set is homomorphic. Note that. Yeah. Note that a plus b root 2 so that AB belongs to Z are okay. I'll make this one. Why this will be homeomorphic to rational, but right now I'm not getting any reference where I can put. Okay, if it's not homeomorphic, okay, just I'll mention it or mail it. It will. Okay. And now problem number 11. This is 11. Problem number 12. What problem number 12 says is that is this problem number 12. Okay, sir. Yeah, I'm sorry, but yeah, this will be. I was thinking that maybe not directly I can see, but right now this is problem number 12. No, this is not problem number 12. Problem number 12 is yeah, this is problem number 12. Consider SON. Consider SONR. SONR, you know the special linear group, that one, and a subgroup. As a subgroup of SONR, what is the SONR model? Do you know that was A inverse that I'll prove a little bit. That okay, how this SONR we know all those A belongs to MNR such that A transpose A is equals to identity and identity n and determinant of A is equals to 1. This is SONR. Okay. Now any A belongs to SONR, I can include it from SON plus 1R by A going to A going to 1 0 0 something like this 0 0 something like this A this is the A. Then what I need to prove is that what is okay. What is SONR mod SONR? That is what homeomorphic to SN. That is what I will prove. That is homeomorphic to SN, I think. Yeah. Let's consider assignment 7, last problem. Yes. Let's consider if from SO n plus 1 R going to the map r to the power n, r to the power n plus 1, how this is going to be? A goes to a e1, where e1 is equals to 1 comma 1 comma 1 0 like this way. This is in rn plus 1. First term is 1, all other term is 0. Then clearly if this is the map. Clearly a e1 inner product a1, that is equals to inner product a transpose a e1 comma e1, that is equals to a transpose is identity a e1 e1, that is equals to inner product e1 e1, that is equals to 1. So that means f of a, that inner product f of a, that is equals to 1. That means mod of f of a, I mean whatever that element. This is, you can look at this, A is a matrix that is going to a column vector, something like this. Okay, so this is the matrix. So this column vector is a inner product of this column vector. I mean this column vector is something like, if it is a11 like a1n plus 1, something like a n plus 1 going to be a n plus 1 n plus 1, so it will be go a11 a n plus 1, something like this, a11 to a n plus 1 to 1. And what is mean? This is means that it's mod summation of a1 I1 square I equals to 1 to n plus 1 is actually 1. That implies that f of s o n plus 1 of r, that means image is sitting inside s of n. That is what. Now what second thing is that now SON is sitting inside here. Now what I will prove here is that NCF reduces a equation continuous bijection from, and also F is continuous, there is no problem. And note that F is also continuous. Note that F is continuous function. Okay, F is also continuous map. So now F is a continuous, and now we will show that this is surjective. How will we show that? Note that F is surjective. How I can show that F is surjective? Let's take a vector. F is surjective means it is continuous. That means F from, I will write is F from, this is S of n sitting inside Rn plus 1. Surjective means as a function F from SO n plus 1 R to S of n. This is surjective. Indeed, for any vector like x1 up to xn plus 1, which is sitting inside Sn, I can get is sitting inside Sn. So that means what it is, that means xi square, that means this is sitting inside xi, means xi square I equals to 1 to n plus 1, that is equals to 1, then this x1 dot dot xn plus 1, this is an orthonormal vector, in r to the power n plus 1. Now we can extend this orthonormal vector v1, extend v1 to get an orthonormal basis v1 dot dot vn plus 1 of r to the power n plus 1. Then this matrix v1 dot dot vn plus 1 automatically, because this is an orthonormal basis, so this is sitting inside so n plus 1r. This is orthonormal basis, so that's why this matrix, this v1 v2 vn, if I replace this is the matrix v1 like this way, so this matrix will be orthogonal, and it is being orthonormal vector, so determinant will be 1 also, there is no problem. Okay, determinant why? If it is determinant is 1, because if we can choose, okay, this is I can say this is belongs to O n plus 1r, right? We can choose v1 dot dot v n plus 1 such that determinant of this orthonormal matrix vn plus 1 1. If determinant is actually not 1, suppose determinant is not 1, what will be? That will be minus 1. Only choice is that. Then take v1 dot dot, change the last one only, just minus vn plus 1, and keep other as it is. Okay, so this one, take this or replace this by this. Okay, I can better to write, then then replace this matrix v1 v2 vn plus 1 by v1 v2 v1 v2 minus vn plus 1. So this is, so my point is that I can always choose a matrix. That means we can get a matrix A is equals to like v1 v2 vn plus 1 sitting inside so n plus 1 r, such that f of a, which is equals to a of e1, which is equals to v1. So that means a from this so n plus 1 r to s of n is surjective. Okay, first fact is this, surjective. First fact is this, f is surjective. And now what I will prove here, basically quotient. So I will do the quotient, and then that will give the all things. This one is homeomorphic, and quotient and surjective, all these things will be automatically done. Okay. Now what I will prove here is that, let's take H is a set here. Uh, H is a set here. What that H set? H set is here. H is the set so n r, but that is sitting inside so n plus 1. How this sitting is giving? That is like this way. Take an element a which is in son, I can consider it element as in s of n plus 1 by just changing the first element 1. Okay, that is what, how this sitting inside son. Now what I will prove, that this h is actually the kernel of this function. We will prove that f is, okay, we'll prove that. Okay, let's see. So what we will prove is that if a u1 or f of a u1 is equals to b u1 for some a b belongs to, for some, okay, let's Recall that f was from S O n plus 1 R to S of n, okay? And now if f of A is equals to f of B, if and only if B inverse A, this is the claim, B inverse A is sitting inside SO n plus 1, but SO n plus 1 as a subset of SO n plus 1, okay? As a subset of, that is what means, as a subset. How this will happen? If f of A is equals to f of B, that implies that A1 is equals to B1. Okay, for if, okay, so basically A and B are coming from SON, so automatically intervene. Let A and B coming from SON plus 1 R, and f of A is equals to f of B. That means AE1 is equals to BE1. That implies B inverse A E1 is equals to E1. Okay, let's take C is the matrix B inverse A, E1 is equals to E1. Okay, then clearly, as A and B in SON plus 1 R, that implies C is equals to B inverse A, that is also being SON plus 1 R. Okay, that is what it is. Now, so C is in SON plus 1 R. So that means C transpose C is equals to identity. Okay. Take C is the matrix, that means C1, C2, Cn plus 1, this n plus 1 column. These are the columns of C. Okay. Now what this means is that suppose I have this C1 transpose, means C1 transpose like Cn plus 1 transpose, this one with C1 with Cn plus 1, this one is equals to identity matrix 1 0 0 something like this way, this is 1 0 0 something like this. Okay, so this is the matrix, so this will give that C of I transpose Cj is equals to 0 if and not, if I is not equals to 0, if I not is equals to j, 1 if I is equals to j. So this is the fact. Okay. So that means now if you this matrix, if you look at this matrix, my point is that this C matrix is something look like this way. 1 comma 0 comma 0 0 comma 0 comma 0 some matrix here, so that is the what I will look at. Okay, but note that C of E1, but C of E1 is equals to E1. Okay, so that means Cj comma E1 is equals to 0 for all j is not equals to 1. How this is happening? So that is what I think little fact we can look at. Okay, so what we have, that C is just to rough, we can look at that C1 T2 Cn, the Cn plus 1. This is the thing. Okay, now with this I am defining inner product, means this will be like 1 comma 0 comma 0 comma 0 something like this. So this will be like, first one will be like C1. Okay, second one will be like C2, so second one will be 0 comma 0 comma 0 something like this, but C1 is 1 here, and all other automatically becoming 0. Okay, so Cj inner product is E1 is automatically becoming 0. That means this column C, okay, I mean, basically, this is means that first entry of Cj is 0. Suppose I have a vector, Cj are the column vectors here, right? E1. So, what my point is that suppose Cj, this is true for all j, okay? For j not equals to 1. So, that means suppose Cj is something like this matrix, okay? And with the inner product of U1, that is 0. So, that means except the first term, all other term is 0. And similarly, if we transpose it or C transpose, here what it is giving, that's this one. So that means I'll get again the all other term 0. So that means I mean first entry of each column is 0. That is what I mean. Okay. But C is orthogonal. So that means it is automatically getting that first column will also be 0. Something like this. Okay. Ci transpose Cj is equals to 0. Okay, so C is equals to something like 1 0 0 0 0 0 0. This is something not known. So that means this is sitting inside H, not H, SOA. But as a subset of, as a subset of SON plus 1 arbitrary. Okay, okay. So this is the thing. Just a minute. Is there any problem? Just let me clear it. F of AB, it can only be inverses. So conversely, that means f of A is equals to f of B implies that B inverse A belongs to SONR. Conversely, if B inverse A belongs to SONR, then f of A is equals to f of B. How can I prove that? Then f of A is equals to f of B. B inverse A is in S of A. That means B inverse A is equals to something like this way, 1 comma 0, some matrix, something like 1 comma 0 comma 0, something 0 0, something like this way. Okay, this is equals to H. So B is equals to H. H is looks like this. Okay, then B is equals to AH, AH. Okay, sorry, A is equals to BH, BH. Then note that AE1 is equals to BHE1, that is automatic. So that means, but note that HE1, note that HE1 is equals to again E1. So that means B1. That means F of A is equals to F of B. So that means what we have proved here is that f of A is equals to f of B if and only B inverse A in SONR. Okay, that is what. So now how this claim is going to help us, that is, so here what we have proved is that basically that f of A equals to f of B if and only B inverse A is in SONR. Okay, so now you can look at this particular Most again. Here I will what I will use the quotient topology and all those things. It is clear that SON is closed subset of SON plus one. That is for sure. And let's define a equivalence relation SON plus one by let A and B two element A and B two element in SON plus one are then then A related to B if and only if B inverse A belongs to SONR. That means as a subset of um, as a subset of SON plus one R. Then this is an equivalence relation. This is an equivalence relation. Check that this is an equivalent relation. That means A related to A itself, A related to B, then B related to A. That is automatic, and A and B related, B and C related, then A and C related. All these things you have to check. Okay, so this is equivalence relation. Okay, check this one. Now then the equivalence classes. Then there exists a quotient topology on SON plus 1 are mod this one. Okay, and and define. So then quotient topology this and a surjective map pi from SON plus 1 R to S of n, right? Now which is pi, this is not SON, this is surjective map from SON plus 1 R mod this. Define a map, define a map F from SON plus 1 R to okay, one more thing here. SONR to S of n by F of A is equals to AE1. We have seen that this is well defined map. We have seen that. Then okay, if I have, suppose I have a subspace, and if this is happened, then this is a name. There is a equivalence relation is name. That equivalence relation, this is called SO. This is same with SON plus 1 R mod SON. This is not same. This is not equivalent. This is same. This is the equivalent relation. This is S of n plus 1 R mod SONR. So what is this? Basically, my point is that suppose G is a group and N be a normal subgroup. I think that is defined. That is already discussed. Let not here, but in sorry, let G be a group and N be a normal subgroup. G mod N is just um, collection of equivalence classes, collection of equivalence classes A related to B, where equivalence relation is given by where relation equivalence relation tilde is given by A related to B if B inverse A belongs to A. Look at the lecture note. I think there it is. Okay. Look at lecture note. Okay, so this is same. That is what my point here. So this is SONR, right? So SON by F of A. Then we have seen that F is constant on each equivalence classes. That means that A and B inverse A is in SONR. That implies that F of A is equals to F of B. Okay. Yeah. Uh, okay. B inverse A belongs to S of NR. That is already seen. That means F is constant on. Now, by the properties of quotient topology, there exists a unique continuous map F naught from SON plus 1 R mod SONR to S of N. How? Just to S of N plus 1 R to this is the pi S of N plus 1 R mod S of N R, and I have a map function F which is continuous, and that is going to be this, and and there exists a unique mode F tilde which is continuous. Clearly note that F is surjective such that F naught compose pi is equals to F. F is surjective. That will imply that F naught is surjective. And if the as F is con and as F is as F of A equals to F of B implies that sorry, as B inverse A belongs to SONR, that will imply that F of A is equals to F of B. That means equivalence classes, I mean, main point that was if and only that F of A equals to F of B, F of A equals to F of B. I mean, they are constant only on if they are constant, then they must be in the same equivalence classes. That is what. So this will imply that F is injective. That means F from SO1 plus R mod SON R is F naught to the F naught to the S of N is a bijective continuous map, and pi similarly pi from S of N R to S of N plus 1 R mod S of N R uh, be a continuous surjective map. This is compact automatically, okay? Surjective map that implies that these two factor implies that f of S O n plus 1 R, it's not f, this is pi, is equals to SO 1 plus R mod SO n R is compact. That means f naught is a bijective continuous function, bijective continuous function from a compact set SON plus 1 R mod SONR to a Hausdorff space, to a Hausdorff space, and that implies that F naught is bijective. Hausdorff space S of n, that implies homeomorphic, that implies F is homeomorphic, F naught is homeomorphic, homeomorphism. That implies that SON plus 1 R mod SON R is is homeomorphic to S of SON. So that implies the main problem if we look at the, so this will be S of n, and as R to the power n and B and this O orthonormal and SNR, they are not homeomorphic, okay? They are not homeomorphic to as R to the power n. I think that was the, what was the options, that R to the power n, SLNR and ONR, as R to the power n or SLNR or ONR are not homeomorphic to SN, then B, what was that? A, B, C. I think three options. No, A, B, and C. A, B, C are not correct. A, B, and C correct. Okay. So this is the this is okay. So this is all. I think okay. If is there any problem, please tell me. I'll try to solve it. Otherwise, I'll discuss some problem related to the 80 content. Okay. I'm sorry for the inconvenience you are facing for again and again. My network is not still here. Okay. So let's. If you have any questions, you can ask. I am meanwhile I am trying to concentrate on the intake to it contents. Okay. So okay, thank you. If you before exam, if you have any problem, questions, you can ask in discussion forum or to my mail ID. I'll try to answer it. Okay. Okay, let's do some 8-week content. Okay, what 8-week content is normal topology? A topological space topological space x tau is called normal is called normal if for any two disjoint closed subset A and B there exist disjoint open set there exist there exists disjoint open sets U and V such that X belongs to such that A is subset of U and B is subset of V. U intersection V is empty. So what we recall that if you recall the definition of Hausdorff space, what that definition says that X and a topological space X is said to be Hausdorff if for any 2 distinct point X and Y there should exist two non-empty open set, there should exist two disjoint open set even this such that X belongs to U and Y belongs to V. That was the thing. So here it is something like this different. So here it is for closed set. Okay. So that is what. So now if you recall, note that if a topological space is normal and so I will just write here. Note that if a topological space normal and singleton set are closed set, singleton sets are closed sets, it's are closed set, then it is automatically housed of it is housed of but a housed of space where singleton sets are closed sets there need not be a that need not be topology normal that I'll come but that will come later but here what is an example of a normal topological space example of a normal topological space that example you can take any metric space. Metric means any metric space. Any metric space. Okay. Now, second is that Urison lemma. Any metric space is an housed up any metric space is normal topological space. Okay. Any metric space, normal topological space. Urison's lemma says that is a normal topological space can be two closed subspace in a normal topological space a closed subspace can be separate. Okay, that is what. Let A and B are two disjoint closed subset in a normal topological space. Normal topological space, then there exists a continuous function okay let's take that normal topological space x tau then there exists a continuous function f from x to 0 1 such that f of um, f of a or f of x is equals to 0 and f of a is 0 you can say f of x is equals to 0 for all x belongs to f and f of x is equals to 1 for all x belongs to B. This is Wilson's lemma. This is very interesting, and this separates. That is me. That means that if you take, suppose I have a function f from x, that is something like this one to the closed interval 0 1, right? So that is saying that the set A is going to be the point 0 and the set B is going to the point 1. So now if you take an interval if you take a neighborhood of 1 and take its inverse image, so that will contain the set B. And if you take an small interval around 0 and take its inverse image, then that will contain the set A. And if the interval, if you which are you are taking here, that means if you just to make sure that this is 0, this is 1, so this is this one and this is this. So now if you take an interval here something like this and here something like this which are disjoint, so if you take that interval and so then their inverse image will be to open set which makes separation. Okay, so now okay, now one more point. First fact, I just want to fact a continuous functions not always maps a compact set, sorry, may not maps a normal set, normal topological space to a normal topological space. Why? How this is true? Let's take Q with the discrete topology, or just a minute. A continuous function need not map a normal topological space to a normal topological space. That is my claim, right? Take natural number, or I can take uh, so natural number. Let x is equals to natural number. Okay, with discrete topology. Okay, discrete topology, and y is equals to also natural number with cofinite topology. Cofinite topology. What is this cofinite topology? That is equals to a set U subset of n is such that all those sets such that complement of this U is either full set, either either full set, either n or a finite set. So cofinite topology is something like um, n minus U is capital N or a finite set. And take f from x to y. Now identity function now f now x as in the left hand side space x has discrete topology, so here f is always continuous. Now as x has discrete topology, as x has discrete topology, f is continuous. But note that x is also normal. Why this is normal? For every closed set, whatever the closed set, I mean, in what is the x is normal. Note that why x is normal, x has discrete topology. So that means every set is closed and every set is open. Suppose I have two disjoint, why? Because suppose I have two disjoint closed set A and B. This is empty and A and B. Now I need to disjoint open set U and B such that A should contain in U and B should contain in V. But take U is equals to A and V is equals to B. They are also open. I mean A is closed, but they are also open again because X has discrete topology. But Y does not, and f of x is equals to y. Note that f of x is equals to y and f of x is equals to y. So this is surjective and bijective function because I am taking identity function. But the topology, but with or y is not y is not normal. Why this is not normal? Take two disjoint sets. Okay. Why this is not normal? This is not normal. You can take suppose let u1 and not u1. Let's take a and b are two closed sets. Then n minus a and n minus b are finite. That was the definition. Take n minus a is equals to some finite set x1, x2, xn, and n minus b, that is some another finite set y1, y2, y2, ym. Okay. Then note that. So um, that means a is subset of natural number. That means after a finite number of term, there will not be term. Something like this is natural number. Suppose 1, 2, 3, something is there. Suppose this is the highest number xn. Okay, xn need not be highest, but there should be a highest number of this set n minus a. Okay. After that, all other points are not in n minus, not in a. Okay, but any two, I mean, whatever two disjoint set, I mean, point is here it is that if we take A and B to our open set, then they are not disjoint. Okay. But but any two open set U1 and U2 are not disjoint. Why? They are not disjoint. As U1 and U2 are open, that means n minus u1. Okay, I don't need to write this one. I don't need this expression. I need what I just want to show that any two non-empty sets are any two non-empty open sets are not disjoint. That is what I want to do. Any two non-empty open set are not disjoint. That is what I want to do. So let u1, u2 are to open. That means n minus u1 is finite. That is equals to, let's take x1, x2, xn, and n minus u2, that is again finite, that is equals to x1, x2, y1, y2, ym. So that means if you take u1, u2 union u2, what you will get? You will get a finite set, and that will be union finite set. Okay. But the point is that, I mean, main point is that, I mean, I can just draw graphically. Suppose this is the natural number. This is the natural number I will denote by, suppose in black. This is 1, this is 2, this is 3, this is 4, like this way. This will be somewhere xn, this will be somewhere ym. Okay. So what here is happening is that un I mean every element after this, suppose maximum. So basically what I want to prove here is that take z is equals to maximum of this set x1 x2 xn and y1 y2 yn. These are natural numbers, so there should exist a finite number of natural number, there should exist a maximum. But for all natural number greater than z, those are will be inside of u1, as well as, I mean, all natural number, something like a statement is something like this: all natural number greater than z are in u1 as well as u2. Why this is happening? What it is saying that n minus u1 is a finite set that x1, x2, xn. Suppose this one the x1, this one x2, something like this is xn, and n1 minus n minus u2, that is finite set y1, y2, yn. Suppose this is y1, this is y1, this is y2, this is yn. Now all other point after this yn or xn, whatever the maximum, all other point these are the already in u1 and as well as already in u2. That means u1 u2 is not disjoint. That means u1 intersection u2 is non-empty. This is true for any open set u1 and u2. But if this is true for any open set u1, u2, so how can we get two open set u1 and u2 such that A should contain in u1 and B should contain in u2, and u1, u2 should be disjoint? So this is for any two disjoint closed set A and B of natural number, we will not be able to find we not be able to find open and disjoint set u1 and u2 such that A should contain in u1 and B should contain in u2 and u1 intersection u2. So that means this thing is not happening. So that is the factor is that we will not be able to find open set this one. Okay, so we will not be able to give this type of things. That means this that means y with so y is equals to natural number with cofinite topology is not y with cofinite topology is not normal. That is what my point. Okay, I hope it is clear. If there is any doubt, you can ask. Okay, now what I will do one more thing here. Okay, and I'll take few more minutes as there is a little problem. Okay, that is very interesting problem I will do here. Let x and y are two topological space. Okay, let's do it for x. Okay, x is this is the topological space. Okay, x is topology. X is a topological space. Okay, let x be a topological space. Let x be a topological space. Just 1 minute. Let X be a topological space. F from X to X and G from X to X are two continuous functions. Then S is equals to all those X belongs to S such that f of x is equals to g of x. Then what is the condition on S? What is the condition on X such that S is closed? Recall that if we take f is a function from x to r and that is continuous, then we can easily note that when f is from f and g, both are then both of them are x to r and g are continuous, then S is equals to all those x belongs to x such that f of x is equals to g of x is closed automatically. Okay. So, but one of the property of this real number R is housed off. So that is what will be needed to set that S is closed. But because it is easy that just take H is equals to F minus J and S is equals to H inverse of the set 0. That is what. Okay. So now here how will prove that? Consider product topology on X. Define a map H from X to this X cross X. How I'll define that H of X is equals to F of X comma G of X, right? Then clearly this set S is nothing but the inverse image of H x comma y, not x comma x, such that x belongs to capital X. This is a subset. Note that x comma x such that x belongs to capital X. This is a subset of this product space. Okay. Now to show S is closed, enough to show this particular set, enough to show that this particular set x comma x such that x belongs to capital X, this is diagonal, subset of x cross x is closed. This is diagonal set, something called diagonal. So when this will be closed, that is the so basically what I am saying, that if we take this set is, if we anyway if we give a condition on x, so we need a condition, so we need a condition on x cross x which will assure that the set x comma x such that x belongs to capital X as a subset of x cross x is closed. Okay. And our claim is that when this is housed off, this will happen when when x is housed off. This will happen. How this will happen? Let x is housed off, right? X is housed of. Then to show x comma x belongs to capital X such that x cross x is open, this is open enough to show the set x comma y such that x and y are coming from x is its complement, that is x comma y such that x is not is equals to y and x and y are coming from x. This is equals to complement of x cross x minus, this is complement, basically this is complement, x cross x minus the set x comma x such that x belongs to x, this is complement is open. Now I am saying that if it is housed up, then this set is open. Why this set is open? This is open. To prove this is open. So to prove this is open. How to prove this is open? Now take 2 point x and y. This one is the set take. This one is the take a name. This is some set A. So enough to show A is open. Okay, this is what. So let's take x belongs to A. That means x is obviously not is equals to y. Then there exists as x is housed of. Then as x is housed of, there exists open set u and v of x such that x belongs to capital U and y belongs to this v, and this u intersection v is non-empty. Sorry, empty. Now, if we take u cross v is an open set in the product topology of x cross x, then and x and y and x and y belongs to u cross v. That means for any point x and y belongs to A, there exists an open set, basic open set, not open set, because this is basic open set in base, open set in basis. There exists an basic open set u cross v such that x and y belongs to u cross v, that is subset of A. That implies A is open. That implies the set x and y, the set x and x such that x belongs to capital X is open in the product topology of x cross m x, and that implies the set f of, that implies the set x belongs to capital S such that f of x not is equals to f of y is in open in X. Yeah, this set is closed in X. This is not equals to, sorry. This set is not equals to, this is equals to. This is that one, fx not equals to y is open. So f of x is equals to f of y is closed in X. So this is okay. Now one more thing I'll just try to do and close our session today. Just today definition. A definition. What definition it is? It is for I think regular space. There was a topological space is called regular. A topological space is called regular if for any disjoint set, for any closed set, physical space x tau is called regular if for any closed set x, sorry, any closed subset, for any closed subset A of x and point x belongs to capital X such that x is not contained in A, there exist two disjoint open set U and V such that x belongs to U and A belongs to V. So where and this U and V are disjoint and U intersection V are disjoint. Okay. Note that so this is another claim you can check. Note that X be a topological space, X with a tau be a topological space, then X comma tau be a topological space, then if singleton set point set, if singleton point set in X tau is closed, then if okay no let's take this is let x tau be a topological space and in which singleton sets are closed. If x tau is regular, that implies that x tau is Hausdorff. So in some sense, if Hausdorff space, I mean, if it is if a topological, if I take a topological space X, and that is the in which every singleton points are closed. So in that situation, a normal topological space is Hausdorff, sorry, regular, and a regular topological space is so if singleton points are so if singleton are point set if singleton point sets are closed in X tau, then X tau is normal implies that X tau is regular implies that X tau is Hausdorff. But there exist Hausdorff space which are not regular and there exist regular topological space which are not normal. Regular topological space which are not normal. For this particular, there exists a Hausdorff topological space which are not regular. We can take a topology. How this topology is taken? Let's take R with tau of R. That means open set, open interval. Let's take how that this is something like take R and let's take k is equals to 1 by n belongs to natural number. Okay, then tau of R, collection of open set, that is equals to all open interval a b such that a less than b and a and b are coming from real number. union of AB, sorry, open interval AB. I mean, basically, this will be there. I mean, this will be pair in pair. That is what my point. Open interval AB and open interval AB minus K, such that A less than B and A and B are R. This will form a topology. So, is a topological space. This is check, which is housed of but not regular. Okay. I think I can stop here. I don't need anything. I need one more thing, but okay, that's okay. But I think this is okay. There is a lots of problem to this lecture. So sorry for that. Okay, is there any questions till now? If if there is any questions, please ask. Otherwise, I will stop in few seconds if there is no any questions.
No, sir. No
Okay.
questions.
Okay, and all the best for your exam. Thank you. Okay, I'll
Thank you,
stop
sir.
here. Yeah, thank you.